Yes.
So we saw that how the charge is distributed if you have given parallel plates. We also saw some of the question in which the plates were connected, and we saw that okay, when the plates are connected, then how the charge consumption is affected. So when the plates are connected, then we saw that we conserve the charge for the connected plates, not for individual plates, right?
Yes.
They will proceed from there. Okay, I hope you remember this simple capacitor in which our charge is given q to one and minus q to other. The charge which will appear on the outermost surface is 0 and 0.
0.
So all of the plus will appear here,
Yes.
and all of the minus will appear here. And what we will get is uniform electric field between the plates. And to find this electric field, we can do a Gaussian surface like this. I hope you remember this Gaussian surface pretty well. And if you draw the Gaussian surface like this, the benefit is on the left side, there is no flux, right? So if on the right, if I assume the net field as E, then the flux will be E into the area of the one of the side, which you can take as whatever value you want. And that will be equals to the charge enclosed, which is sigma into A dash.
For absolute.
So the E turns out to be sigma by epsilon naught. Now E is representing the resultant field. It is not the field of one of the plate. It is the net field due to the both the plates. Because whatever we obtain by the Gauss law is the resultant. If you want to solve by the individual plate concept, then so each plate will create a field of sigma by 2 epsilon naught, and both will add up to make it again sigma by epsilon naught. I hope this is clear.
Yes.
Yes, sir.
It is always advisable to use the Gauss law instead of going through the individual one, because we always looking for the resultant electric field, and the Gauss law is meant for giving you the resultant field, not the individual field. Okay. So if we have multiple plates, then how we are going to get the capacitance of a combination of plates? So let's put a heading. So capacitance of combination of parallel plates So we have plates like this. And if these are plates, let's say the outermost plates are ground are connected by some connecting wire, and we are supposed to find the capacitance between the terminals like A and B. So the question is, what is the capacitance of A and B? Okay, so first of all, we need to understand that okay, A and B, if I ask as a capacitance across C of A and B, so A and B will act as terminal, and the rest will be the common, some simply arrangement of the plates. So when I say A and B are terminal, it means the potential must be applied across A and B. So to solve a question like this, we hypothetically assume, let's say some potential is there. So a battery of voltage V we apply here. We assume the potential difference to be NB. And the moment you assume a potential, what battery does? Battery will take a charge from some charge from here and will give it to the other. So the role of battery is to take charge from one and give it to other and keep it as it is. So once it is given, it will be stored there, and battery will prevent the reverse flow. That is what the battery does. So in a way, we are doing the same thing. We are giving a charge of value plus Q to one, and I'm giving the charge of value minus Q to the other. Understood?
Yes.
So this is what we are doing. Okay. Now, once you give charge Q to one and minus Q to other, and the outermost is not given any charge because these are not connected to a cell. So the outermost we can call as a isolated connector as a whole. I mean, not individually, but if I take the first and the second together, we can say the two are isolated connectors. So the rule says that the net charge on any isolated system of connector is always 0. So I think we have discussed this rule, right, in the last lecture. Now, once you give charge Q, the question is how much charge will appear on the this side and how much will appear on this side. Can we say Q by 2 will appear? Can we say?
Sir, but here the net will be like 0, right?
Yeah, so outermost will have 0.
Okay. Yes.
How we are going to distribute here? The problem is, let's say the gap is D and D. So you have given charge Q, that's good too. I mean, that's good. Okay, it's given to the one of the plate connected. But do we know the distribution on the right and left of the same plate? Yes or no? We know the total is Q. Do we know the values on the right and left? The answer is no. We don't. So how to begin with? So we call, let's call this is Q. So what is the here value?
Q minus Q.
And similarly, if you this is Q, the facing will be minus.
Yes.
So this will be minus Q plus small q.
Yeah.
So the facing will be opposite. So this is Q minus, and this is minus Q plus Q. The opposite of facing, right?
Yes.
And now you can see everything is satisfied now. The charge conservation, the charge distribution. Okay. So when you connect a battery across two plates, what you do is it is similar to the act of giving plus Q to one and minus Q to other. Okay. So a battery is giving how much charge? So when it is said that okay, how much charge is being given by the battery. So we look for the positive plate, like the plate which is connected to the positive terminal, and we see the charge. And we can see here the charge given is Q here. So we say that a plus Q charge is given to the plate. We always say the charge given to plate for the positive terminal plate. We never say the word that, okay, it is taken away of minus Q. So it is taken Q charge from the one of the plate and given to other. We simply say a charge of value capital Q is given to the plate. So what we really look for is the positive terminal, and we see this is connected here. So we say that a charge of value Q is given to the plate which is connected. Always we say this way. So we never talk about from whom we have taken. We only say what is given. That is idea. Is this clear?
Yes.
Yes.
So once we have this, we have one unknown value which is small, correct? And as long as we have this unknown value, probably we cannot solve, right? So this we can write as a minus of Q minus Q. This is better way of writing. And this we can write better as, correct? Now let's represent the field between the plates one by one. So for the leftmost pair, the field will be, can we say like this? If I choose this as positive and this as negative.
Yes.
Between the middle one, can we say like this?
Left to right. Yes.
And again here. And because you can see the charge pair on the left and the rightmost are same, isn't it?
Yeah.
And the gap
Yes.
is same.
Yeah.
So if this is E1, I can I say this is also E1,
Yes.
Yes.
but this is, we can say E2.
Hmm.
Now, if you begin from the leftmost plate and if you reach the rightmost plate, the potential must be same. So if I choose the potential of this as V1, can we say this is also V1?
Yes.
So what we do is we go from leftmost to the rightmost and we write the equation because we know they are equal. So beginning from the leftmost V1, if I move next step ahead, so we need to move against the field, right?
Yes.
E1.
Yeah.
So the potential will rise
Hmm.
by value E1t. Yes
Yeah.
or no?
Yes. Sir.
And the
So-
next will decay by E2t
Hmm.
because we are moving along the field, and it will again rise by E1t. And then we are back to V1, right?
Yes, sir.
Yeah.
So beginning from V1, the rise and fall, if you keep on writing till the plate, we know that this is equal, so this will cancel out. So what we are getting is 2E1 equals to E2. Yes or no?
Yes. Sir.
Yes.
And we know from Gauss law how to write E1 and E2. So what is the E1 value? E1 is, so we just read this. What is E1?
Sigma by
So what is sigma here?
Q minus Q.
by A absolute.
And what is E2? Same formula
Q.
by.
A
A
epsilon.
absolute.
So can we solve this? And once you solve, you can see the answer is 2Q by 3, right?
Yes, sir.
Yeah.
So we are done. Now the next thing which we can write is the potential difference will be how much? So you can see this voltage is between the plate, the middle plates, right?
E to D.
E to D. And because we know the charge value, I can add E2 is how much?
It's Q by A epsilon.
But what is Q value? Q itself is 2Q by 3.
Yes.
But we know that the C equivalent is defined as charge given upon potential difference, isn't it?
Yes.
So Q by V turns out to be how much? 3 by 2 epsilon 8 by epsilon 3 by 2.
Yes,
Do you
sir.
get the answer? By
Yes.
definition, if a battery of voltage V has given a charge Q, then the C equivalent is we write as Q by V. Is this clear?
Yes, sir.
Yes.
Now, this is a very basic way of solving. This is the scratch method. We have very simple way of solving this. I'll give you the trick method, which you can also apply to get the answer. But this is a way in which you can see every event. You can see how charges are getting distributed, how charge conservation is being followed, and so on. So when we have the combination of plates given to us, and if they show the terminal that choose this and this as the terminal, the simple rule is connect the battery, give a charge plus Q minus Q, and then proceed the way we proceeded here. Okay. So for your practice, I'll give you one more question, and hopefully you should be able to solve.
Yes.
Just- So here is the question. So generally what they do is they draw the connector just like this. One plate, two plates, two, and now these two plates are connected like this. And this is my terminal. So proceed the way we proceeded earlier and try to find the answer. Assuming that every plate having the A area and every gap is D. Okay,
Yes.
Yes, sir.
try this out. If you want, you can draw it vertically also, but I just drew the way it was given.
Hello.
Yes.
Sir, I think I'm getting it 2A epsilon naught by D.
2A, not by D. No. So now you have to connect a battery between A and B, right?
Yes.
I hope you have done like something like this.
Yes.
The V is here. So the charge will go here, Q.
So.
This will have minus Q charge
Yes, correct.
in total. But how the charge will distribute across the plate on the two sides? So we don't know.
We will take Q.
So let's say we take Q here, minus Q, Q minus Q,
Yes, sir.
and this will be how much? Okay, we don't know.
Yes.
As of now, we don't know. But we know here, this is how much? This plate is minus Q only, na? And there is only one surface because the outermost will have 0 for sure. So if this is minus Q, this must be how much?
Minus Q.
Minus. This must be
Q.
the facing surface must be equal, na?
Yes.
So if this is plus Q and this is minus Q, so that's fine. So what about this one, this plate? It is minus.
Q minus Q.
Let's add the value. Is it 0 if I add for this plate and this plate together?
Yes, sir.
And if you look at carefully, these two are isolated, right?
Yeah.
So plate number 1 and the plate number 2 are like 2, 3. So plate 1 and 3 are isolated. So the net charge on the 1 and 3, the sum of charge on 1, charge on plate 1 plus 2 must be 0, right? Is this clear?
Yes, sir.
Yeah.
So you can show the electric field up, down, down,
Down.
and all three will have different values, right? We cannot say E1, E2, E3. I mean, E1 equals to E1. If I say this is E1, this is E2, and the last one is E3, right?
Yes, because the charge distribution.
Correct, because you can say pairwise charges are different. But what we know is that if you move from this plate to 1 to 3, the potential must be same, right?
Yes.
So what will be your first equation if you go from 1 to 3? So if we move from plate 1 to plate 3, if we move from plate 1 to plate 3, what we can write? V1
P1 plus E1D minus E2D minus.
E3.
Yes.
No. We are
But
done.
it will not come.
No, we are done with the.
Yes.
This is equals to V1. So basically, E1 turns out to be E2. And if E1 turns out to be E2, then we can say the charge must be same, right?
Yes, sir.
So Q minus Q must be Q.
Yeah.
We are writing the formula. So Q turns out to be Q by 2.
Sir, I got this only. Q is equal to Q by 2.
So now how to write the V1, the V part? The voltage V is across 2 and 4, no?
Correct.
So how to write from 2 and 4? You have to walk from this plate to this plate. So if I call for plate 2 and 4, I'm writing, look at this carefully. So I'll just write like in a loop. So I'll move from here to here. I'll move like this, like this, like this, and we'll come back. Okay. So look at this carefully. You simply walk like this in this path. So the way of writing is simple. Can I write minus e to d? I'm walking from 2 to 3 first. Then minus e3d. Again, there is a drop. And if you come back through the battery part, it will be plus b.
Yes.
It's the same thing, right?
Yeah.
Equals to 0. It's like loop. I'm moving in a loop. Okay, this is difficult to understand. Or can I test? Let's call this as V2. Potential of the plate number 2 minus E2D minus E3D equals to V4. Okay. So what is V2 minus V4? What is V2 and V4 difference? Capital V, isn't it?
Yeah.
So it's the same thing.
Yes.
Okay. What is E2? It's Q by A epsilon. What is E3? It's Q by A epsilon into T. And Q is Q by 2. So this will become how much? Q by 2 A epsilon. Q by A epsilon into T. This is 3 by 2. So basically Q by V is how much? 2
C.
by 3, which is C equivalent, right?
Yeah.
So the answer is C equivalent is 2/3 of epsilon naught A by D. How many of you have realized this? Raise your hand if you have already understood this. Very few. So Aditya, Archit, Atharv, Garv, Harshit, Kanu, and Manasvi. So all of you have not understood?
No, sir, I'm trying.
Ask me if you have any doubt that where you got stuck, which part.
Sir, I got it.
Okay, good. So have you all understood this? Shall I move to the next concept?
So
Yes.
Okay. So your next concept is solve the previous question. Now, okay. Everyone, please do solve it. Until you're not able to get it, keep on solving. I can wait. Let me redraw here for your reference. Don't copy and paste, try to really solve it and try to get for yourself. So I think this was the question. Assume charge, distribute the charge, write the equation. See, are you really getting it? Or are you getting stuck again? So this practice is very, very important for you. Later on, we will have a simpler way of solving these questions, but I want you to learn from the scratch. Now, why this method is interesting? Because let's say there is a comprehension type question in which we have to answer a variety of questions like find charge, find electric field, find so and so. So if the C equivalent is the only one question to be asked, to be answered, then we have a trick for that. But if we come across multiple questions based on the same question, then in that case, the scratch method is better because we can answer a variety of questions in a given question. Okay, so one question will have the equivalent of 3 or 4 questions like find the field between the plate 2 and 3, 3 and 4, 1 and 3. Okay. So in a comprehension type question or in the multiple choice questions in which we have multiple answers pertaining to the same question, okay, probably you will go with this method. If the only question is to find the C equivalent, then the trick part which I am discussing again and again, okay, that we have to use. Anyway, so this.
Sir, I solved it. Okay.
Okay, so getting the same answer, I hope so.
Yes, sir.
Very good. So anybody else able to reciprocate the same? None is there. It is very important for you to actually master this. So how many of you are able to get it? Raise your hand. Just one. So do I need to explain again? Hello, guys.
So please wait for a moment.
Look at this. See for yourself and try to understand what is happening here. and then again repeat till you're getting it right. If you're not getting it right, repeat. So there is no way out. We have to do the dirty job. We have to write things, get the answer. Is the method clear now? So what we do is like whenever we have the plates with same potential, we move from that plate to that plate and we write the potential same, which gives the first relation. The next thing is we move across the plate such that the battery is involved. So we move from one plate to the other plate across which battery is connected. So we get the second equation, and I think that is sufficient. The two equation will give us the voltage in terms of charge, and so the ratio we can get the answer. So if I ask you like question like what is the charge on the plate? Let's see if I number the plate. 1, 2, 3, 4. So what is the charge on the plate 1? Yes, so that is the question. Charge on
Q minus.
it is minus of Q minus Q,
Yes.
which is minus Q by 2. Correct?
Yes, sir.
So they may ask the question like what is the charge on the plate 4? You can see it's a minus Q.
Minus Q.
So what is the charge appearing on the facing plate of 2 and 3? The positive value. It's plus Q by 2, right?
Yes.
So multiple question can be asked based on the charge distribution. Anyway. So what is the status now? How many of you have understood? Raise your hand. Those who have understood, please raise your hand. Everyone, keep your hand raised. Atharv, Garv, and Harshit. Not understood? Okay. Okay, so those who have understood will again, okay, will not solve this question. I'll give you a new question. So remove this. So here is your question. 1, 2, 3, 4, and these two are connected and these two. And the battery is connected in a very nice way. It's connected across this combination. Okay. Same A, we have to take as A and D as acceptance. Find everything. The charge on the plate 1 and 4. Let's try one. So what is the charge on the plate 1 and plate 4? How to begin with? So charge, okay, this is, I'll do a bit. Yeah, you can keep on solving. I'm just drawing it. Bit. And the gap I'm going to take as D only. So check whether you're getting the idea here or not. So tell me the answer.
Sir,
Yeah.
sir, I did the distribution part. But
So what will happen? The charge will come here is Q.
yeah, like the whole will have the Q, right?
Yeah,
Minus
whole
Q.
will have, but we don't
Yeah.
know how much will go there or there.
Yeah.
So the best way to start is from the outermost plate. Why? Because the outermost will have minus Q is the net, but outermost will have 0 here.
0, 0. Huh, correct.
So if I assume some value here Q, this will be minus Q minus Q, right?
Yes.
So that is done. That's like we know the answer, and therefore the facing plate we know the answer. So the facing will have Q plus Q and minus Q. The only thing left is if you add these two charges, you can see it is already plus Q,
Yes.
which means nothing will appear here, right?
Yeah, correct.
So we got the distribution done.
Okay.
So we started with the outer one and we realized that, okay, the the middle two plates are already following the charge conservation, and therefore we don't have charge more than that we need to think about. So can we say net is 0 in between the plates?
Yes, sir.
Imagine if you're not able to figure it out.
Sir, I took two variables and solved.
Yeah, that's fine. That's fine. That is also okay. That's why I'm saying. Imagine if someone is not able to figure it out that, okay, something is not between the facing plate of the middle plates. Okay. So in that case, you will assume something like x and minus x. Because even if you assume x and minus x, we are done. No? It's the same thing. The conservation is still the same. Okay. Okay. So the middle one we can assume x and minus x. I think we need to assume it. And now we can solve. We have two variables, so we need two equations for sure. Okay. Now what we know that if the potential of this is V, this must be V.
Yes.
And if this is V dash, this is also V dash. And V minus V dash is V. Okay, let me change the name. Confusion 1. Okay, just a minute. Just to make a better assumption. Carefully. If this is V1, this is also V1. Yes or no?
Yes.
And if this is V2, this is also V2. Yes or no?
Yes.
And can we say V1 minus V2 is capital V? Yes or no?
Yes.
So what are the steps there to be taken? You have to walk from V to V. So you can walk from here to here, then here. So the field will be like this. One, let's take like this. E1, E2, E3. So let's go from V2 to V2. V2 minus E1D minus E2D equals to how much? Equals to V2 only, no? Okay. So what we're getting here answer? E1 plus E2 plus E3 equals to 0. And I can say Q plus X plus Q. So can I write like this?
Yes.
You can choose X and Y also. That's a nice way of writing. Anyway, this is the question number 1. And If you go from V1 to V1, it is only E to D, but E to D must be 0,
Yes.
which means E2 must be 0.
Yeah.
Because anyway, between equal potential, we can't get any charge. So that means the X is 0.
X is 0.
So that's your equation 2. And that's why I say anyway X will be 0. Even if you don't believe it, it's going to be 0. So between the two parallel plate having same potential, can we expect any field first of all? If the plates are same potential, then can we expect any field between them?
No.
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 So X was 0 by many logic, but nevertheless you can do it mathematically. Is this clear so far?
So,
And now we are done with the answer. So Q is how much? Minus Q by 2.
yes.
Okay. All right. And then we have to use this equation somehow. So I'll walk from here to here. This difference. The E3D is nothing but the capital D, isn't it? V1 minus E3D is V2. Why we are writing this equation? Because we have to use the V somehow in the equation. Why? Because V is given in the question. What is not given? Yeah, this is given. The charges are not given. Okay, so we have to find everything else in terms of V only. So V1 minus V2 is E3D. Okay. And this is capital V. So E3 is how much? Tell me. What is E3, guys? It's how much? Come on, what is E3?
Q
Hello?
plus Q by A.
Yeah, absolutely.
And small q we got, na?
It will be Q by 2 though.
So the answer will be Q by 2. And therefore we can get the Q value because V is given. So answer is 2A epsilon V by 2. Isn't it? So we got the charge, right?
Yes. Sir.
In terms of potential. So the last step is what? The last step is what? Well, okay, they're asking find charge on plate 1 and 4. 1, 2, 3. So charge on plate 1 is how much? It is Q,
Q by 2.
which is minus Q by 2,
Yes.
which is minus A epsilon naught V by T. Isn't it?
Yes, sir.
And charge on plate 4. So plate 4 is minus Q plus
Minus
Q,
Q by 2.
which is minus Q by 2. No, minus. This is, yeah, minus.
Yes.
Yeah. So it's the same answer.
Yeah.
Just a minute. Q is minus Q by 2. Q plus minus Q. Okay. Yeah. Okay. Yeah, fine. Yes, that's the again same answer. So I hope this is clear.
Yes,
everyone?
sir. I got the correct answer. Yeah.
Very good. So if you are clear with this question, then just to practice a bit more. So how many of you have understood this part? I know this is difficult. It's not very easy.
Sir, can you show the previous slide?
Yes, I can show. If this is done, then I can proceed to something new.
Yes, sir, done.
So let's begin by drawing the plates. 1, 2, 3, 4, 5. Now I just inserted one more. The difference is only one extra plate is now introduced. The rest is same. Okay. So what is given? The V is given. So can you do the all arrangement and how to begin with, how to start the assumption, what to do, what not to do? Can you do it now?
Yes.
Go ahead. Mm. So once you're done, then I'll just name it. 1, 2, 3, 4, 5. Okay, now numbering will be like this. So maybe I will ask question: charge on the plate 1, charge on the plate 4, charge on the plate 5, maybe. Okay. So find the charge distribution on every plate. Let me put a question. So only 5 minutes.
Hello.
Yeah, tell me.
Sir, I think I did it.
So tell me the answer. Okay, tell me the charge values at every plate. For the plate one,
Like in
just plate one, plate one. Tell me, charge is how much?
minus q by 2 means minus a epsilon naught v by d.
Is it coming minus? Yeah, it is minus.
Yeah, it is coming minus.
Very good. So minus epsilon not a v by d, right?
Yes.
Can you tell me what is potential? I'm saying, what is the charge here? The fourth plate.
It is 0.
Fourth plate. The total charge. This side, both.
Acha, total. Total minus a e epsilon naught v by d. Positive.
This positive is correct, but it is I think twice of the value, previous value. So I will time up. I'll not solve. So again, the same, the process remains same. I'll always start with the outermost, right? Because this is 0, we know. And the 1 and the 5th will have the net will be minus q, right? So if I say this is x, this will be how much?
minus q minus 6.
So the
Yes.
first part is this is minus x. This is q plus x. Now here we cannot say 0 because the middle one will change the scenario. So I don't know what is this, but I need to assume something like here. This is assume y here. Why? Because the plate is isolated. So if I choose y on one side, the other must be minus y. Yes or no?
Yes, sir.
If I choose y on one side, the other must be minus y because the net is 0. And again, the facing plate we can write as y and y. It is clear.
Yes.
If you do this distribution of charge, then you will be able to get it easily. So you can pat yourself if you have got the distribution correctly.
Yes, sir.
Very good. So how many of you got the distribution part only? That is more than enough. For that you will get almost 100 marks.
I got it.
Very good. So getting the correct distribution itself is a big deal. Then okay, the next part is solving. So we have to start something like this. We know that V1 must be V5, right? And V2 must be V4. So we have two equations, and then the last is like I can choose any one. The 4 and 5 difference is how much? V, right? So these are the governing equation because of course we have how many variables we have? We have two variables x and y. So we need two equations to get x and y in terms of q. And then to relate the q with voltage, we need the third equation, which is, so basically there are three variables, small capital Q, small x, small y. So the total number of variable if you count is q. So do you realize the variable?
Yes.
The only thing given is
V.
so all these answers must be a function of v, correct? And of course dimension also a and d. I should have done, but no. So knowing the constraint And the equation, let's say 1 and 2 are the constraint and 3 is the equation. Can you solve it? Or you can say all 3 are equation. Can you solve it now? So you have to just draw the electric field, right? E1, E2, E3, whatever.
Yes.
So E1, E2, E3, E4, right? I think I'm correct. E1, E2,
Sir,
E2.
for the third to fourth, I think you did it opposite.
Ah, my bad. Big mistake. Can we say both as E2 and E2? Can we say because it's symmetrical?
Yes.
Then E1, E2, E2, E3, right? Just a minute. All right. So the next step is you will tell me what the equation 1 implies. 1 implies what? Tell me. Anyone? What 1 implies? So if you try to use the equation 1, you have to go from first plate to the fifth plate.
Yes.
So if you go, what will write? Minus E1D plus E2D plus E2D minus E3D
Minus E3D.
equals to 0.
Yes.
So can we write? Okay, I'll write E1D now. Why we need to write like this? Because imagine if they change the separation also, then D1 will not cancel out. Okay, so you will have some coefficient of D1, D2 also in the answer. But luckily here things are simple. This is E2 only. My bad. E2D. So the answer is how much? 2E2. Twice of E2 is E1 plus E3. Isn't it? And now let's substitute the value. What is E2, guys? Tell me, what is E2?
Y by A epsilon naught.
What is E1?
X by A epsilon naught.
What is
Q
E3?
plus X by A epsilon naught.
So 2y equals to 2x plus q, right?
Yes.
So I can write y minus x equals to q by 2. Just call it equation number 4. Yeah. Okay, so similarly, if I got one equation 1 for the first equation, can you do it for the 2 and tell me the
Yes.
answer? Yeah, please do it. See, until you will not try, these things will appear difficult. Once you try, this is not difficult. And probably you're solving the toughest question. I'm saying these are the toughest part from this chapter. The rest will be quite easier. Nothing is going to be as difficult as this.
Sir, I'm getting Y is 0.
Okay. Y is 0. All right. Yeah, Y is going to be 0 only.
Yes.
Correct. So now you got everything, huh? Because Y is 0, so X is
Yes, sir. Minus Q by 2.
minus Q by 2. That's done. And then you can use the equation number 3. 4 minus 5 is V, which will give you directly answer. U plus X by A epsilon naught into D equals to V, right?
Yes.
So because I have a space here, I will solve it here. So can we write like the 2 equals to 4 will give you the 0 answer for sure, because E2 is in the same direction, which means if
Yes.
E2 is in the same direction, which means 2 and 4 will have potential difference, which is not possible, right? So that means E2 must be 0, which you can also verify by writing. So 2 implies that 2E2D is 0, right? Do you realize this?
Yes.
So okay, Y is 0, and because Y is 0, so 4 implies Y is 0, so 0 minus X is Q by 2. And then the 3 implies that Q plus X by NX we know. So
You get QS. That's it.
the answer is 2A option or V by D, right?
Yes, sir.
Okay, so we got everything, no? We got all answer. So what is the charge on the plate 1?
Minus
is
A
minus-
epsilon naught V by.
Correct.
Yes.
So charge on plate 1 is X, which is minus Q, which is minus, and the charge on plate let's say 4 is how much? So Y is 0, so it's Q plus X, which is plus Q by 2, right? Isn't it?
Yeah. Yes.
So
K by epsilon naught. Sir, I got the same answer.
yeah, that's it. So we can move to the next concept, which is very, very important. That's called dielectric. We have discussed the dielectric before? No. Have we discussed before about dielectric between the plates?
No.
So today's discussion is dielectric. So what is dielectric? So this is basically made of 2 words, dia plus electric. And if you know the organic chemistry nomenclature, you know that when you add 2 English words, and if the ends are and beginning are vowels, the first vowel is
Yes, sir.
removed, and that's why the word is dielectric. So this is some etymology, and dia basically means through. So a medium through which electric field can pass is called dielectric. I hope this is clear.
Yeah.
Okay, so the dielectric is basically a medium through which electric field can pass, because it is in contrast with the conductor in which electric field cannot pass. Okay, so when I say conductor, we know inherently that electric field cannot pass, so that's why it's a not dielectric, it is conductor. And dielectric is not a conductor, which means it is insulator. Okay, and the property of insulator is that it will let the electric field to pass through it. Okay, so that's the difference between the dielectric and a conductor. So the other name for dielectric is insulator. Okay, so insulator allows the field to pass, conductor do not allows the field to pass. I hope this is clear.
Yes, sir.
Yes.
So a medium through which electric field can pass is called dielectric. And now how they allow the medium to pass? Because they try to stop, but they cannot stop completely, as opposed to the conductor, which can completely oppose the field and cancel the field in totality, and therefore we have the zero electric field between the in the bulk of conductor. Okay, so there are two types of dielectric that we will come across. The first is called the polar dielectric. Another is called the non-polar. So polar dielectric and non-polar dielectric. What is polar one? So we say if a molecule, if you remember the dipole chapter in electrostatics, if a molecule is having dipole moment non-zero, and if a medium is comprised of such molecule, so every molecule will have dipole moment and the medium is comprised of such molecule. But in the medium, these dipoles are randomly oriented. So PM so although individually they are not a zero, but if you add all the values, the medium as a whole will exhibit the zero dipole moment, because of the random orientation will cancel out each other, and because the numbers are infinite, so we can say this medium is a dielectric and this is a polar dielectric. But why? Because every molecule will have some intrinsic dipole moment, and because the vector summation is zero, so the medium as a whole will not have the dipole moment. This is the elementary volume basically. Even in the elementary volume, you will find infinite number of dipoles. And if I add it up, it must give us zero. So we call such medium as polar dielectric. We have also, okay, now let's give some example. What are the examples of polar dielectric? Any molecule which is having non-zero dipole moment. So tell me the examples. HCl is polar or non-polar?
Polar.
Polar. H2O,
Polar.
you can say HCl aqueous. It is still polar. Water is anyway polar. H2O, polar. CH4, What is CH4? Is it polar? Come on.
Non-polar.
It is non-polar.
Yes.
Okay, so there are many. You can take any molecule, HCl, HBr, uh, any halogen with hydrogen. Okay, so all are polar molecules. H2S, sulfur. Ammonia is
No.
ammonia is also polar, right?
Yes.
NO2. All are polar. Come on.
Polar.
Anyway, these are polars. Okay, so non-polar is what? In which individually every element, every molecule is zero. And if individually it is zero, the medium will have nothing, right? So how we represent them? By drawing the circle. So because I'm tired, what I'll do? See, smart move. So now you can just draw like this, plus minus, plus minus, plus minus. So individually every molecule will have zero dipole moment, because the center of plus and center of minus charge will coincide, right? If you remember the dipole chapter.
Yeah.
Don't remember?
Remember.
Nothing. Yeah, very good. So this the LHS we can redraw as like drawing ovals, right? So the diagram which is typically available in the books are like the ovals. And then we have the so in case of a polar dielectric, we represent by oval shape. And how we represent the non-polar? The round shape. Okay. So when you see these diagrams for the next time in the textbook, it should not surprise you why it is so. Now we are supposed to study about the properties of dielectric only under the influence of uniform electric field. So the heading is dielectric in uniform electric. Particularly, we have to understand in terms of capacitor. Like what happens if I insert a dielectric between the plates of a capacitor? So inserting a dipole, inserting a dielectric between the plates of a capacitor, so it will completely occupy the space. I'm leaving no space, but still for some illustration purpose, I am bringing some gap into the diagram just for the sake of illustration. It is not actually present. So now if a dielectric is filled between the plate of a capacitor, it will be a really nice cuboidal shaped dielectric, right? And we have two terminals. Oh. So these are the terminals. You can connect a battery if you want, but as of now, this is imagine a charge you give here is plus Q, the old fashioned way, minus Q. So the charge that will appear on the outermost plate is, and all of the charge will appear on the innermost plate.
Yes.
So when we represent this in a circuit, we simply draw a capacitor like this, and we represent charge here, which is actually present in the inner plate. Okay, but this is how we represent on a circuit. So in circuit, the way we represent is not the actual representation of charge or actual presence of charge. This is called circuitry representation. So nothing appears on the outer surface. What appears is on the facing surface of capacitor. Is this clear?
Yes, sir.
So one
Yes.
should not be confused with the circuit and the actual diagram. Okay, so on the left, what you see is the reality. On the right is the way we have symbolized the circuit notation. Anyway. Now, as of now, you can see I haven't shown either ovals or the X because I'm not trying to distinguish whether it is a polar one or whether it is non-polar one. Okay. So although visibly nothing is represented, but what you need to understand, either oval or the X are present in the volume of dielectric, isn't it? So oval means it is a polar one, and the X are like the round shapes are like ovals and circles. So circles are meant for
Non-polar.
non-polar. Now, no matter which dielectric you use, the behavior will be somewhat similar. The mechanism will be different. So when a dipole is kept in external electric field, let's say we know that the plate is going to create external electric field for the dielectric as a medium pole, right? So can we say that the field developed by the plate of capacitor is like this? Yes
Yeah.
or no?
Yes, sir.
So now I'm not representing the resultant field, I'm representing the field due to the plate. And the field due to plate we take as the external field for the dielectric. Is this clear?
Yes.
Yes, sir. So this electric field we call EP, and I'll just put the legend here. So EP is basically electric field due to charge on the plate. Now imagine if you assume an oval shaped polar dielectric and the field is like this, EP. So what you realize, or maybe you don't realize, that a dipole is kept in external electric field. And we know that if a dipole is kept in external electric field, what will happen? A torque will be acting on it, and the torque we write as P E sine
Sin
theta.
theta.
So the P vector is like this, E is like this. So P cross E, that is the form of a torque, P cross E.
Yes.
Yes.
So you can see P cross E is what, clockwise, isn't it?
Yeah.
Which means every dipole will try to align itself in the direction of field. Okay. So the randomness will be disturbed, isn't it?
Yeah.
Yes.
So no longer we will have all dipoles exactly random to make the net field 0. Rather, there is going to be a lot of alignment, and we are going to get some really aligned dipoles along the field. Even if it is not, we can say there is a net component along the applied field, isn't it? What does it mean? It means this dielectric will make it small, just to save my time. So all the ovals will be oriented like this. Hold on. So we can say that under the influence of external field, which is developed by the plate, will make something like this arrangement, isn't it? And we say,
Yeah.
Yes.
okay. And what happens as a result of this, that the medium which was neutral, the medium which was electrically neutral, when the same medium is brought in external field, it is no longer neutral. So now we see that the dipoles are linearly aligned. That's a way of thinking. It is not the reality, because dipoles are not free to turn as per their will. There's some resistance also. Yeah, if it is a liquid dielectric, then it is quite possible that it will be actually aligned, because in liquid it is easy to turn, right? If it is solid, let's say if I freeze into ice, the alignment will not be as much as for the water, although the properties are same. Because we know there is something called the H bond in ice, and the H bond will kind of like a constraint relation. It's like you bring some more constant, you decrease the freedom. So every constant we put, we always decrease the freedom. Anyway, what you realize that if this is the arrangement, if I believe this is the arrangement, then this plus and this minus will compensate each other. So the bulk will compensate the charges, but what will not get compensated? The edges, right? So the arrow sign of minus and plus is representing compensated compensate. What does this mean? ACT, ACT,
SATE.
ACT. Yeah. So this is called the compensated charges. And then the boundary charge, which I'll represent like this. And charge on the left, this we call okay, uncompensated charge. So we have the compensated and uncompensated charges. And what we realize that a medium will actually create a charge layer on its extreme point. Okay. And therefore, I can redraw here. I have a space. I just want to utilize it. So this entire medium will have a negative charge here and a positive charge here. So do you realize this? Why this is happening? Hello, hello. Is this clear?
Yes.
Okay. So apart from the applied field, if I just draw the field one by one, this was the field which we had already, the field of the plate. But this plus charge and this minus charge, which are equal and opposite. So this charge layer will internally create its own electric field, isn't it? Do you realize this?
Yeah.
Yes.
And but this field, the scope of this field will be its volume itself, because it will terminate on its own negative charge beginning from the positive charge. So the scope of the field that the dielectric will create is the dielectric itself, the medium itself. So the moment you come here, the only field available here is which field? The field of the plate. What is the field here? The field of the plate.
Field of the plate.
What is field here? There are two superposition. Okay. Because this field was not present, it only got induced when you kept this medium in an external field. So this field is called induced field. And this itself, the induced field, you can think as a two separate layer of charge, which is the medium itself will behave as a distinct capacity. Now this charge we can call as minus sigma dash because it's induced charge. This we can call plus sigma. Why? Because the plate sigma will be different from this sigma. Understood?
Yes.
So the plate will have sigma and okay. Okay. Now you may argue that why the sigma and sigma dash are not equal. If it is exactly equal, it is not a dielectric, it is a conductor. Because if sigma and sigma dash are equal, then all lines of force will terminate here only, isn't it?
Yes.
So nothing can go through the medium. Yes or no?
Yes.
And if nothing can go through the medium, then can we say this as dielectric? There is nothing like
No.
dia. It's a conductor then. So
Yes.
the the property of dielectric is that they are not capable of cancelling the charge completely, cancelling the field lines completely. They only cancel partially, and therefore that's why they are dielectric. Dielectric. Electric field can go through them. If it will cancel everything, then nothing can go. We can say. Okay. So when I say go through them, it means that there is a resultant field is still available, but that is going to be weaker than the actual field, isn't it? So actually we have two layers of charge. So within a dielectric, when we keep a dielectric between the plates of capacitor, then the charge density on the plate will be more than the charge density on the dielectric surface. So the induced will be less than the applied. So there is a net value left. And how to find the net value? Using the principle of superposition. Hello, hello.
Yes.
Yes.
Principle of superposition. So let me do one second. And this is the most difficult part for you to grab here. If you can grab here, then probably this chapter will have nothing to offer you in terms of difficulty. The rest are application of some trivial concepts. All right. So, okay, one second. Plus, 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 minus, 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 minus. Whereas in case of dielectric, the induction is partial as compared to. So the induced charge is not as much as the facing charge on the plate, right?
Yeah.
Sigma, sigma dash, plus sigma dash, minus sigma. And numerically, sigma is more than sigma dash. Is this okay?
Yes.
All right. So now, because we are completely filling the gap, so can we say the area of the dielectric is same as that of the plate? Can we say yes or no?
Yeah.
All right. Now, from the Coulomb's law, we know that the resultant field. So right now we can say there are two fields. I mean, let me draw the same thing again. This we call the EP, if you remember. Okay.
Yes.
And this we called E induced. Oh, my bad, my bad. So what is the net field between the plates?
EP
Net
minus
EP
field.
minus E induced.
Very good. Net field between the plates. Just a moment. Okay. So net field between the plate. Okay. Or if I ask you, that's a wrong question. Better I can say the net field in the dielectric. The net field in the dielectric. Because the scope of E induced is what? Dielectric itself. That's a better if I write it here, right? Scope of E induced is dielectric itself, right?
Yeah.
So we need to remember that the scope of the electric field of dielectric is the dielectric itself. Therefore, beyond its volume, the field will be only due to the plate. So you can say just outside the dielectric, the field that we get is due to plate. Is this clear, guys?
Yes.
Okay, so I have mentioned this explicitly, though not required. Nevertheless. So can we write the net equals to EP minus E induced? Okay.
Yeah.
Yes.
Now we know that the net field is given by the formula, the field of the plate upon dielectric constant. And that comes from the Coulomb's law, because if you remember the Coulomb's law in dielectric, the formula was 1 by 4 pi epsilon naught epsilon R. And I have proved this also in the previous lecture. Yeah, in dipole I have proved it already. But in a medium, the field will decrease. So in vacuum it is 1 by 4 pi epsilon naught. In a medium it is. So the electrostatic force we write by this formula. And the Coulomb's force we write by formula like this. And I told you, okay, Coulomb's law gives the ability to interact with each other, assuming if kept in vacuum. And the electrostatics gives the actual force. And the actual force is not due to the charge on charge, but it is due to the charge on charge and medium on charge. So the role of medium is inherently compensated in this formula. And that's why this term comes. So the electric field is how much, guys? So I can write as E induced is how much? That's a better way of writing. Is this clear? Yes.
Yes. Sir.
So E induced we can write as, because in terms of sigma we know the answer for capacitor, right? So if I ignore everything else, let's say if we have just dielectric and we have plus charge minus charge, so the plus and minus will act as a capacitor. And what will be the electric field due to the plus charge minus charge? We know the answer.
Sigma by epsilon.
Sigma by
Epsilon.
epsilon, which is sigma dash by.
Epsilon.
It is epsilon. See, there is nothing like epsilon.
Yes.
Epsilon only comes when we don't write the medium contribution explicitly. So when we want to write what medium is doing, if I'm writing sigma dash, I need not to write k. The k will come automatically, and the EP will be sigma by epsilon. Is this clear?
Yes.
So you can see the
Yes.
induced charge is how much? It is the actual charge density. So this is the first formula. The second relation is if I multiply this equation with area, because it is same area, also sigma dash into A equals to sigma into A. And we can see it's facing completely. So can we say how much? Q dash equals to, let's call Q. Into 1 minus 1 by epsilon. Can we say like this?
Yes, sir.
Yes.
Now I'll introduce you something called dipole moment of a medium. Okay. So what is the dipole moment of a medium? Dipole moment of dielectric. Let's call it small p. So small p is how much? Can we write sigma dash into A into the separation D?
Yes.
Because the dipole moment is what? Charge into separation, right? Charge is how much? Sigma dash into A. But if you look carefully, this is sigma dash into AD. Okay.
Yeah.
But AD is a volume. AD is volume. So we have a very nice term in electrostatics which I have discussed. Polarization. Polarization, which we write as capital P. So polarization is defined as induced dipole moment in a medium per unit volume. That's the definition. How much dipole moment you have induced in a volume, and therefore the polarization we can write as P by volume, isn't it? So this we got as okay. Let's write the value first separately. So the numerically in magnitude, you can write P as sigma dash AD upon volume is how much? So you can see volume itself is AD, isn't it?
Yes.
So basically the polarization is nothing but the surface charge density of induced charge, right? So a dielectric which is kept between the medium, this is the polarization. It is clear? Sigma dash.
Yes.
Okay. So the E net we got how much? If you remember what is E net? The E net we got is
EP
EP
times.
minus E induced, right?
Yeah.
And EP and E net we have a relation. So this is equation 1, and we know that E net is EP by epsilon r. So now I want to write the EP in terms of E net. Okay. So from 1 and 2, from 1 and 2, okay, E net equals to epsilon r E net minus E induced. So what is E induced, by the way? Can we attack this minus 1 into E net?
Yes.
And E induced is how much? We know this is sigma dash by
Epsilon r.
epsilon. So from here, the E induced, sorry, we have already written sigma dash. So sigma dash upon epsilon naught is equals to epsilon r1 into E net. So sigma dash is how much? And by definition, sigma dash is nothing but the polarization. So we can say polarization equals to epsilon naught. Is this clear, guys?
Yes, sir.
And therefore the polarization we write as epsilon naught susceptibility into E net, where this is called electric susceptibility. So susceptibility is like sensitivity, how sensitive you are towards the applied field. That's the whole idea. Okay. So this is the formula for the polarization vector is the resultant field. So this is what I used to derive the second form of Gauss law, if you remember the last lecture of electrostatics. So now from capacitor we can see it better, right? So you can revisit that topic of Gauss law which we discussed. Okay. Just one. So now coming back to the dielectric again, we got various formula. Let me summarize all the formula. And you are supposed to remember these formulas. First of all, the E net is always E plate by epsilon R. Sometimes we write the dielectric constant as K. So in case of JEE questions, they use K very often instead of using epsilon R. If you are solving erodive, they use epsilon R more often than K. Second formula. The sigma induced is how much? Sigma 1 minus 1 by K, right?
Yes.
If the area of the facing plate with the dielectric is complete, it's like fully occupied. So the Q induced is also this is only true for conditional apply. I think this is sufficient. So now we can go to the actual topic. The actual topic is okay. What will be the discussion in case of non-polar dielectric? For polar, we have shown like this. For non-polar, what will happen? For non-polar, the moment you apply the field, what to expect? The egg becomes, the circle becomes oval, right? Because of the stretch. So plus will go towards right and minus will go left. So under the action of field will transform like this, and that is why this is called the induced dipole moment. This is not a dipole, this is induced. Induced dipole. Once the induction is done, the rest discussion is same. The compensation, the non-compensated charge or uncompensated charge will appear on the interface, right, left or right. The bulk will compensate. I hope this is clear. So any doubt in this so far?
Yes, sir.
You have doubt?
Clear.
Clear. So what is the capacitance of a parallel plate capacitor filled with dielectric capacitance? Capacitance of a capacitor filled with dielectric. So quickly, So we always begin with the field of the plate, but because the dielectric is completely filled, the moment you leave the plate, you enter the dielectric, right? So what is the field here? This K is the dielectric. Can we write like this as sigma by? So the net field in the medium is how much? K by sigma by K epsilon naught? Yes or no?
Yeah.
So as a thumb rule, what you need to remember is that the moment you enter a medium, the field will reduce by K times. The moment you enter the medium, the field will reduce by K times. The moment you enter the medium, the field will reduce by K times. The moment you enter a medium, the field will reduce by K times. This was the special effect anyway. I hope this you remember. So now to find the potential difference, what we do? So what is the potential difference between the plate? Delta V is how much? The value. It is ED, right?
Yeah.
But what is E?
Sigma by K epsilon.
And sigma we can write as Q by area, right?
Yes.
So the capacitance by definition is charge given upon potential difference. And we are done. Nothing big deal about the formula. It is simply saying that the capacitance will increase by K times, assuming K is constant, isn't it?
Yes.
So earlier the C was epsilon not A by T. Now this is K times. So we can say the C dielectric is K times CAF. Is this clear?
Yes, sir.
Yes.
So it's pretty easy. Again, we will come to these questions again using the simple circuit method. But you must understand this way first. So imagine we have a parallel plate capacitor with dielectric not occupying the full space, rather partially occupying the space. So let's say this is only T thickness and the full is B. And the dielectric constant is K. So how to find the capacitance? So if you go from the plate 1 to plate 2, what part of the plate will have the actual field? The length between the gap with the E field, the EP. Okay, so again you can choose plus Q, minus Q, and whatever. Sorry. So field here is how much? Sigma by epsilon.
Yes.
Here is same, but here it is. Do you realize this?
Yes, sir.
Then you can add the
Yeah.
delta V. No? Delta V is how much? Sigma by epsilon naught is occupying the length D minus C. And sigma by K epsilon naught is occupying the length only T.
T.
So this is the potential difference. Do you realize this? Yes or no?
Yes.
Okay. So delta V we can write eventually as we can take common as sigma by. So D minus T plus T by K. And we know that sigma we can write as Q by area. So C is defined as Q by delta V. So this is the answer. Is this clear? How to derive it?
Yes.
Okay, derive it once again. Solve it without looking at. Everyone, write down the equation. I can check for randomly for anyone. You can send me on WhatsApp quickly without delay. So 2 minutes to solve this question.
Sir, done.
Those who have done, raise your hand. Only one. Are you guys finding this really difficult, challenging? So those who find this really challenging, not able to understand anything, raise your hand. Okay. So those who believe that okay, they have understood, but to apply, they need to work at home. Raise your hand. Okay. So you will practice at home. Okay, that's your duty. Make sure that before the next lecture, you are master of all these questions. So you should be as fluent as your teacher is. Okay. Let's do the next question. Let's stop the lecture after 2-3 questions. Don't worry. So the dielectric part is, I know it's a bit difficult, but trust me, these are the typical questions of JEE also. What if I insert a metal? So what if it is conductor? Can you tell me the capacitance value of this arrangement?
So the metal is conductor, right? So
So what? Metal is conductor, we all know. Okay, anyway, you solve it and let me know the answer. If it is a metallic connector, let's call. Tell me, is it that difficult?
Yes.
The process remains same. No? You will walk from left plate to right plate to write the potential difference. So first step is always same. You assume some charge on the plate, you write the field, and then you move from left to right, and you keep on writing the delta. And what you are supposed to use is ED, correct?
Hello.
Yes.
A E epsilon naught by D by minus T.
minus T. T minus T.
Okay.
Yeah.
Epsilon A by dimension. So it is like the conductor will reduce the gap by its thickness because it will offer no field, right?
Yes.
So nothing, no difference will appear across the plate, right? This to this.
Yes.
It's like a short circuiting the gap, right? So it
Yeah.
is equivalent of a parallel plate with the only gap D minus T, right? With air. So we can add the answer is the D is replaced by D minus T. I hope this is clear.
So,
Yes.
Also, you can remember that the for metallic conductors, K tends to infinity for the obvious reason. Sigma by K epsilon is filled, but this is zero. Now, when this is zero,
When K tends to infinity.
so even in this formula, if you put K tends to infinity, we get the same answer. You can check, isn't it?
Yes.
yes.
If I connect these two plates with the help of a conducting wire, the C will be
Infinite.
because delta V is zero, no?
Yeah.
Yes.
Got it. So these are some typical questions, and one last question to end today's lecture. So K1 and K2 are dielectric. Okay. Can we find the answer? It's the same process. In the blue region, what is the field value in terms of sigma?
Sigma by K1.
Very good.
Epsilon
K1
naught.
epsilon naught. And in the other part,
Sigma by K2 epsilon.
and then you know how to walk, right?
Yes, sir.
Do it.
Sir, I got the answer.
Yeah. Then
2a epsilon naught upon D 1 by K1 plus 1 by K2.
like this.
Like 1 by K1 term is in the denominator.
Like this only. This is the answer.
Yes.
So this we can write as okay. This is entirely below.
That I'm telling.
Like this.
Yes, sir.
I think this is correct. So we can write this as 2K1 K2. Is this the answer?
Yeah, I got this. Yes, sir.
Very good. Now, if this is the answer, so they will ask you find the K equivalent of the capacitor. What does it mean? What if I want to replace by a single dielectric? What K will give you the same capacitance? So what K we
So,
must
K
choose?
equivalent will be K1 plus K2 divided by K1 K2.
Yeah, twice value, right?
Yeah.
2 K1 K2, right? Yeah, correct. So if I say this is K equivalent, the D remains same, A remains same. So the C in terms of this will be K equivalent A up naught by D, correct? And we just compare these two equations. See, epsilon naught A by D is the famous answer. So you can just remember that this is for air. So whatever is the coefficient is acting as the K equivalent, right?
Yeah.
So K equivalent here means what value of equivalent dielectric that we can insert, which will offer the same capacitance as the combination is offering right now. Is this clear?
Yes, sir.
Okay. So
Yes.
with this, I will end today's lecture. There is no homework because almost every question we have solved here itself. Okay. So there is nothing left actually. We have solved Europe question. We have solved the JEE old question, advanced question, and till here. Okay. The topic that I have taught. Now in the next lecture will have something more deeper, more thoughtful. So we'll see the more deep down the concept of dielectric, and we'll solve more questions. Okay. Bye and take care,
Yes, sir.
guys.
Thank you, sir.
Thank
Today's
you.
lecture, you all have to practice today's
Yeah.
lecture itself. Okay, that's it.
Yes, sir.
That is homework.